So welcome to our YouTube channel. Today we'll explore how physics evolved from classical world to Newton's to the mysterious quantum world of particles. This is the topic today we are going to discuss. That is nothing but transition from classical to quantum physics. So moving on to the journey from classical to quantum physics, from 1600s to 1800s, science was ruled by Newton and Maxwell. So everything seemed predictable. If you know the force, you could calculate where an object would go. This was the age of certainty, which we call it as deterministic world. But around 1990s, things changed. So scientists started studying very tiny particles. Already we know electrons, atoms, and light particles, also we call it as photons, and realized that these didn't behave like big objects. So Max Planck in 1900 said that energy comes in small packets called quanta. And in later in 1905, Einstein showed that light can act like particles, which we call it as photons. So in 1913, Bohr explained electrons move in fixed orbits. So and finally Heisenberg and Schrodinger built full quantum theory in 1920s. So what is the difference? So classical physics explains big objects, as you can assume cars or planets, but whereas quantum physics explains very tiny things, like already we discussed in earlier slide, atoms and electrons or photons or light particles, etc., whatever we call. Okay, so classical world gives exact results while quantum world gives probabilities that you need to remember. Okay, for example, let us talk about one example. I can simply say, if a coin is tossed, so there are two possible outcomes. One is heads and another one is tails. So in classical world or in classical physics, we say either it will be one output, that is nothing but heads or tails. But how this quantum works is nothing but, so quantum says that a particle can be either zero, that is nothing but head or tail, or it can be in superposition, or we call it as both states at a time. So simple example, again think of a coin is spinning in the air. So we'll be having two probabilities when it is tossing in the air, that are nothing but heads and tails. So that we call it as superposition. So I will going to discuss in the next slide what is superposition. Okay, so this is the small example. You can see the difference. On the left we have the smooth slope representing classical physics. Everything moves smoothly and predictably. On the right hand side, you can see we have a quantum step. Energy levels are not smooth, they come in jumps. Okay, that's why we call it as quantized energy. And if energy comes in steps, we call it as quantization or quantized energy. So this is how the quantum looks like. So welcome to the strange but fascinating quantum world. So moving on to some key differences, let us quickly summarize. uh, Classical physics works for big objects, that I have said earlier. Quantum physics works for small particles. What are those particles? That you know, atoms, photons, electrons, etc. So classical laws are deterministic. Deterministic is nothing but we know exactly what will happen in the future. Okay, so whereas quantum laws are probabilistic, so we only know the chances, only the probabilities, I can say simply. So if we observe, there will be no effect in classical physics, whereas in quantum physics, just observing something can change the result. Remember this line, classical is equal to certain, whereas quantum is equal to a question mark or probability. So think of it like this. In the classical world, imagine rolling a ball. So you can easily track its position and speed. But in quantum world, imagine an electron. It does not move like a ball. It's more like a fuzzy cloud. So you can't say exactly where it is, only where it might be you can think. That's magic, and that's the mystery of the quantum world. So why quantum physics matters? Nowadays everyone is saying like we need to learn quantum, we need to learn quantum. Why it matters? So why we should care about quantum physics today? So because it's the foundation of modern technology. The screens we use, lasers, LEDs, and even MRI scans, all are built using quantum principles. This you need to remember. So, and most importantly, it is the base of the future, such as quantum computers, quantum communication, and quantum sensors. So, the quantum world is small, strange, but it powers the future. That is why we need to learn quantum. So, this is about the topic transition from classical to quantum. So, thank you, guys.